in this lecture we are going to talk about FPGA implementation of constant on off time mixed signal current mode control, and we will also demonstrate a short video live demonstration of our hardware prototype. So, here we will first talk about the mixed signal on time current mode control and FPGA implementation aspect of the same. Then we will talk about mixed signal off time constant off time current mode control and then FPGA implementation aspect. So, here both the cases we will be considering fixed current reference. So, we are not going to close the loop, and then we want to justify what is the current loop stability aspect using experimental result. So, if we talk about mixed signal current mode control, this we have discussed I think in week 2 in the architecture, as well as week 3 where we have made the MATLAB simulation. And if we consider this DC-DC converter in the buck converter, then we have discussed that this part is our ADC voltage feedback gain, because we have this resistive divider. Then ADC data is sending, here we are using an ADC clock which is 25 megahertz clock. This is a very high frequency clock, I would say, but you can reduce it, and we are taking the data at the rate of the switching frequency. That means, at every edge of the switching frequency we are capturing the data, and that register output is our output in. This thing we have explained in the context of fixed frequency current mode control. All these terms are common, the D2A, all these things are common. If you go to I think lecture number 75 and 76, I think 75, 76 we have explained peak current mode, mixed signal current mode control, where we have used fixed frequency control. Here the differences will come here. So, this will be the difference, only difference will be coming here. So, here is the difference. So, in fixed frequency peak current mode control we have used here trailing edge modulator, but now here we are using a constant on time modulation, constant on time modulator, in which we are also considering minimum off time. Okay. Now, how does it work? And if you go to our lecture number 95, we have already discussed in detail how to implement constant on time with minimum off time using Verilog code, and then we have also synthesized using for FPGA prototyping. Okay. So, we have already discussed in lecture number 95. So, what is in this case, I mean, if you consider the constant on time control, how does it work? So, suppose we have this current reference and this is our inductor current. When it hit the current reference, then the on time is started. Once the on time is elapsed, then it start falling, and this is the methodology. So, here your on time will be triggered, it will remain on and so on, and this is our T on duration. This is our IREP. So, we are using fixed current reference, that means here we may not close, we are not going to close the loop. So, we are using a fixed value, that means we are using IREP to be a fixed value, and which is going as a data input to the DAC, and this is my IREP. Next, what will happen? Since our comparator is set like this, that means whenever this is my V sense and this is my, let us say we are talking about the comparator symbol here, then what is our, this is our VP. Whenever V sense is try to go below, that means if you see, if V sense is higher than VP, then your comparator will be turned on, right. So, as long as V sense is higher than VP, the comparator is always on, but when VP goes below VSN, then this comparator should be off. So, we are trying to detect here, that means what is the comp output? If you take the comp output, since VSN is always above VP, so comp output is always high. okay, it will go low for a very short duration, then come back. So, this is a comp output. That is why we have inverted. So, this is like your, you can say QTR. Then what is QTR? If I take the inverted logic, it will be just this thing and take, okay, and this is what we expect for triggering the monoshot timer. That means, because we cannot change the hardware, whatever is set, the comparator positive and negative terminal, which can be used to implement constant off time, constant on time, fixed frequency, anything. So, only we have to adjust the logic of the comparator output. So, we have said this is my QTR. So, whenever QTR goes high, then the monoshot timer will be triggered, and we have already discussed about the inside block of the constant on time modulator, and it also has a minimum of time, and this is your Q out, and which is going to the input to the dead time circuit, and dead time will generate your PWM high and low. And we have discussed about the synthesis of constant on time modulator in lecture number 95. So, one can go detail to that 95 lecture. So, now we are going to consider some hardware results. So, in this hardware result, we will take the power stage, and we have inductor, this thing we have discussed multiple times. Input voltage will vary to show. Output voltage, we are using a fixed reference. So, there is no point to output voltage because it may not be regulated. We are using a fixed current reference, fixed current reference, and we will discuss what is the exact value of the current reference. So, if we now go to the next, first we are taking the current reference to be 2 ampere, because it is a valley current, it is a valley current reference. Because it is constant on time control, and this is the experimental result. So, you can see this is 1 ampere. So, this line is sort of, it is like 2 ampere. So, the valley current, and because since there is a comparator delay, that is it may cross a little bit, but at 2.5 volt input, and we have set a constant on time T on to be 2.4 microsecond, and we have set a minimum of time of 100 nanosecond, which is 0.1 microsecond. So, it is clear from here that we have set the 2.4 in such a way, if the voltage goes to 1 volt or it is just above, it is very close to 250 kilohertz, sorry 200 kilohertz. This is this peak, I will say this fundamental component, this is like your fundamental, this will be approximately equal to 200 kilohertz. It is not exactly, but approximately 200 kilohertz. Nevertheless, it is perfectly stable, because you can see the fundamental harmonics etc. coming. Now, we decrease the input voltage from 2.5 to 2.25. What you will find that your valley currents remain same, input voltage has decreased, but what has changed? You see the frequency is slightly changing, because it is no longer 200 kilohertz, it has slightly, because this division in the frequency is 250. So, this each division will be 50. So, it is just slightly above 200 kilohertz, maybe 210 or something like that, but it is perfectly stable. And then we have further decreased to 2 volt, that means your input voltage is further reduced, and but duty is large, but you see the frequency is now slowly approaching towards 250 kilohertz, and if you make it at 1.9, it is more or less 250 kilohertz is your switching frequency, which means we found the switching frequency is sort of inversely proportional to V in. That means, if V in decreases, switching frequency increases, but in all cases reference valley current remains same, but the switching frequency is changing, and as a result ripple is changing here, because it is, if you remember what is the current ripple under constant on time, it is M1 into T on. T on is fixed. What is M1? V in minus V0 by L. Since we kept the valley current same and we have certain load resistance, so naturally the ripple will vary because output is decreasing. So, ripple will if the output decreases, then the ripple will decrease, and that is what. So, if you compare the first ripple, so this is the highest ripple, you can see the ripple is almost it's around, this is 1 ampere, it is roughly around 1.4 ampere current ripple, but here it is almost 1 ampere. So, ripple is decreasing. Now, we want to compare 2.5 volt, 2.2 volt and 2.2 volt. So, you see the current ripple. So, the delta IL, actually delta IL is decreasing in this axis if the input voltage, and since delta IL is decreasing, so the frequency is also increasing. And what is decreasing? So, here input voltage is decreasing. So, it is a decreasing Vin, okay, decreasing Vin. So, in this direction the input voltage is decreasing, but in all cases it is stable, since we are using only a valley current fixed reference, no closed loop control. So, that is why you can see the voltage regulation is affected. Now, if we go to constant off time control, then we know about this architecture, which is explained in week 2 as well as week 3 in MATLAB simulation. Then again, if we go, you will find that there is a current reference. So, this is similar to a peak current mode control, but it is actually a peak current mode control, but instead of fixed frequency you have a constant modulator. Now, here we are using a constant on time modulator only, constant on time modulator, which has a minimum of time, but we are inverting the logic. So, that means if this output is Q out, that means Q out goes high. So, and we want this Q. So, our Q should be, what is the Q? So, this Q should be high, it will be low, and this is our off time. So, that means whatever modulator we are setting on time, the time duration, this is nothing but the constant off time. Okay. And if we maintain a minimum off time, it will become a minimum on time for constant off time. So, everything is perfect. And earlier we saw, we took the inverted logic of comp and directly pass Q, but here it is just the opposite. We have to take the comp output directly as the input because our polarity remains same, but we have inverted the output logic, but we are using the same modulator. So, that is the beauty, that means the same modulator using. So, if you want to move from constant on time to constant off time in your hardware, in your digital circuit, you have to just complement this signal and this signal, and you may upload the parameter of the timing parameter accordingly, because in lecture number 95 we have discussed that how, that means to generate this timing parameter we need what? We need an n timer. So, this value if you update, then accordingly your on time and off time can be adjusted in real time, because it is just you update the value in the counter, that is it. So, that means it will happen immediately, and you can reconfigure from constant on time to constant off time just by changing this comp. You directly pass and invert this logic, and in constant on time we will invert comp, but pass this logic, that is it. So, here again if you recall the same logic, I mean we are talking about, and we have discussed in lecture number 95. So, this part will be in our FPGA, this will be coming outside, here also this whole part will be FPGA. So, this part, then this part, this whole part will be in the FPGA. So, this will be in FPGA, and we will synthesize using Verilog. So, now we are going to show hardware results. So, again this hardware result we have considered the same converter, but input voltage will vary. We are not going to regulate the output voltage, because we are setting a fixed current reference, and it is constant off time control. So, if I show the waveform, this is constant off time control. So, then what we are doing compared to the, so this is our, so we are fixing this time to be off, to be fixed. Okay. Now we are going to show experimental result using mixed signal constant off time control, and you know this is a peak current mode control where we are fixing the peak current, and this is our peak current mode control, and we are fixing this constant off time T off, and we are considering T off to be 2.6 microsecond. Now this is an experimental result with 2.5 volt input, and this peak current is 3.4 ampere, and you will see the stable perfect behavior, and it is more or less coming to be around 200 kilohertz. So it is coming more or less at 200 kilohertz. Now if we decrease the input voltage 2.5, it still remains 3.4 ampere, and interestingly you will find that this ripple remains same, because if you go here, if you see the ripple, it is around how much it is coming, around 1.6 ampere. Here also you will get 1.6 ampere, ripple remains same. But what you will find here, the peak was coming in the second dot. Now here you will see it is slowly shifting, but not perfectly visible. But if you go next, this peak is shifting towards this side, which means the frequency is decreasing. That means because we have further decreased the input voltage, it was 2.5, then but it is perfectly stable. But if you go to 2 volt, it is also perfectly stable, peak current difference same, and the current ripple also remain more or less 1.6 ampere, but the frequency is decreasing. So what we learn, if the output voltage more or less maintained, what is delta IL? It is nothing but M2 into T off, and what is M2? It is V0 by L into T off. So if you maintain the fixed current difference, and if your off time is fixed, inductor is fixed, then it will try to regulate the output voltage even though input voltage is changing. So that is the beautiful thing about constant off time control, because if you are going for a precise current regulation, you know, and you have, let us say, a driving LED driver, or you are talking about a battery charger, so you can just use a constant off time control, and if you want to set, suppose this is my desired current average, so I will set the reference current to be I average plus delta IL by 2. Since delta IL by 2 depends on your what is your desired output voltage, and you know the inductor value, so you accordingly set the off time, and then you can precisely control this. Suppose if you want to vary because you need to regulate some switching frequency, then you have to accordingly adjust the reference current. So these things can be adjusted in digital domain very effectively, and beautiful thing, you can have a very wide utility operation, because if you see from 2.5 to 2.25 and 2 volt, 50% is your current loop is perfectly stable. Since we are using constant off time control where the ripple current is more or less same, you see the 3 cases, so the output voltage you can see they are more or less regulated, even though we have not closed the outer loop, it is just a peak current reference, outer loop is open. But this was not the case of constant on time, which will be the case of constant on time for a boost converter, but for a buck converter, for constant off time, the output voltage will be more or less regulated indirectly even without closing the loop, but you still need a feedback to disturbance rejection, even accurate current regulation. But here it will make your integrator job very easy, and it is stable for all periodic behavior. But what is the drawback here? You can see for decreasing input voltage, the switching frequency is shifting. So this guy is shifting, and that's why if when you go to the comparative study, we will see that what is the impact. That means in case of switching frequency is proportional to some way input voltage. That means the input voltage decreases, switching frequency decreases. It may not be linearly proportional, but in the incremental sense they have some linear relationship. So now we are going to consider a live demonstration of hardware implementation of constant on off time control, mixed signal current mode control. Now we are going to show mixed signal current mode control, constant on time as well as constant off time control. So this program actually, I have already demonstrated the process of dumping the code, so I am not going to show it again. This code actually consists of both, because we have already demonstrated constant on time, modulator, everything in detail. So here we are using a current reference fix, that means the only closed inner current loop, outer loop is open. So we are using two configurations in the class, in the lecture we have demonstrated that one is constant on time, where we are using a valley current difference of 2 ampere, another is a constant off time, where we are using a peak current difference of 3.4 ampere. And first, this code actually is made where by changing the switch position we can actually move from constant on time to off time, so we do not need to run the code once again. So this code we have already run, we have generated the program file, and we have dumped this code into this FPGA. Now we are directly going to the hardware setup, and we want to demonstrate whatever we have studied in today's class. First, I am turning on this power supply. So this is the main power supply, and we are starting with 2.5 volt input, and that we have demonstrated. So here you can see that we are first talking about constant on time valley current mode control. That means we are mixed signal current mode control, where the current loop is closed, and we are using a valley current difference of 2 ampere, and you can see that this division is 1 ampere. So this 2 ampere, it is the valley current. So we are fixing the valley current. Now we are changing the input voltage. At 2.5 volt, you can see this frequency, it is more or less 200 kilohertz, because the first peak is coming, the fundamental component here. This is the average current, then the harmonics are coming. Now once we go to 2.25, 2.25 input voltage, you can see it is perfectly stable, and the frequency is slowly moving towards this. That means if I show the process of movement, 2.5 to, slowly that peak is shifting. So you can see the peak is shifting to this is 2.5, and this 2.5, the peak is coming slightly, it is now coming like in between 200 to 250 kilohertz. So maybe it is around 210 kilohertz or so, but it is perfectly stable because the duty is quite large. And you can see, but what another point you will see, the ripple has got reduced. So as a result, the frequency is increasing. If we further decrease, that means from 2.25 to 2.2 that we have demonstrated in the class, we are now coming to 2. So at 2 volt input, now the frequency is coming close to almost 250 kilohertz, it is around 240, and you can see it is perfectly stable, the valley current is maintained, but the ripple is changing, because we have learned in valley current mode control, or basically constant on time control, if you, for a buck converter, if you decrease the input voltage, the ripple current reduces and your switching frequency increases. So the switching frequency is inversely proportional to the input voltage, and as a result peak is shifting, but it is perfectly stable. And if you go to 1.9, so it is also perfectly stable, and frequency is further increased. So now it is become 250 kilohertz is the effective switching frequency. So what we learned, that in constant on time current mode control, the valley current is fixed and current loop is perfectly stable irrespective of the duty ratio, and but the frequency is varying as well as the ripple is varying. Now under the same condition, we are moving to constant off time control, and this is a switch. If you change this button, now it moved to constant off time, where we have maintained the peak current difference, and this peak current is maintained at 3.4 ampere. Now we are starting with 1.9 volt input, that is a least input voltage, and you can see in this condition, when you switch from constant on time, that constant on time the frequency effectively was roughly around 250 kilohertz, but when you go to constant off time, the frequency now has become, because it is 50 kilohertz, so it is like 150 kilohertz. That means it is lower than 200 kilohertz, which is the nominal frequency that we set. But the current loop is perfectly stable, and there is a large duty ratio, there is no instability, peak current is fixed. Now we are increasing the input voltage to 2 volt. So we are getting to 1.9 volt to 2 volt. The current loop is still stable, but frequency is now slowly increasing. But another point, when you go to 2.25, that means further increasing, 2.25, current loop is perfectly stable, frequency has now reached to 200 kilohertz, close to that, but you will find the current ripple is remain more or less same, because if you talk about constant off time, since the off time is fixed and the falling slope is V0 by L, and since the V0 is more or less maintained, so the ripple is maintained, so the ripple is not changing. That's why we discussed that this will be a very good example of LED driver or etc., where you want a precise current regulation. Now if you go to 2.5 ampere, 2.5 volt input, then it is perfectly stable and the switching frequency is slowly, it is slightly above that 250 kilohertz. So that means it's 200 kilohertz. So maybe this may be the reason that we have not set it properly. So we need to, okay. That means this offset is slightly shifted, otherwise this is designed at 250 kilohertz. So we saw that in case of constant off time, the ripple is more or less constant if the output voltage is maintained, even though you vary the input voltage, but the switching frequency varies because higher input voltage, here the switching frequency is increasing, okay, which was the opposite for constant on time. But nevertheless, for both constant on time and off time, you don't need any ramp compensation. The current loop is perfectly stable. Now we will move to our lecture. So just now we have completed the live demonstration of mixed signal peak current mode and valley current mode control for using constant on time and off time. We have shown mixed signal current mode control architecture, their aspect of FPGA implementation, then constant off time mixed signal current mode control and their FPGA implementation. So in the subsequent lecture, we want to take a comparative study between all three control architecture and see what are their benefits and drawbacks. That's it for today. Thank you very much.